This is a short movie to explain how to derive angle information from basic coordinates in 2D analysis. So on the screen at the moment we just have a line which might represent the segment of the human body, and at each end of the segment there's an x and a y coordinate which would locate that segmental endpoint in two-dimensional space. Now we know that actually we can construct this right angle triangle on the basis of that segment, and the sides of the right angle triangle could be known simply by looking at the differences in the positions of the coordinates. So for example, the side being identified on the screen at the moment is going to be measured using the length represented by the difference in the y coordinates, so y2 minus y1, and the side that I'm identifying at the moment on the screen, the horizontal side, would have a length equivalent to x2 minus x1. Now if we have two sides of a right angle triangle, as we'll see in a minute, then that gives us the potential for working out the angle which is indicated here. We could also calculate the other angle at the top there, but we'll see this one perhaps is the one which in terms of conventions is the one we might be interested in. Okay, so let's move on to the next stage. Now we know that we can identify these segments in two-dimensional space with their coordinates, and there are a variety of different conventions that might be applied when calculating angles. Now what we see on the screen at the moment is what we might term segment angles. So if we just show this diagram, here we see a representation of the body, and we note that for a segment angle this is normally measured from a fixed reference, in this case horizontal reference, round in an anti-clockwise direction until it meets the segment itself. Now this fixed reference could be positioned at either the proximal end, so for the upper leg proximal end would be this end I'm indicating on the screen, or the distal end. For the purposes of this movie we're going to actually just think about the distal end, i.e. the end of the segment furthest away from the centre of the body. So in this case an upper leg segment will be represented by the angle measured from the fixed reference round in an anti-clockwise direction until the segment is actually located. Similarly, the lower leg segment would be measured from a fixed reference at the distal end round in an anti-clockwise direction, and similarly if we were just defining a foot segment, then we could locate a fixed reference at the toe, measure round in an anti-clockwise direction. Okay, so now let's bring the two ideas that we've discussed so far together. So we noted that in the first figure that we looked at that we could describe the lengths of the right angle triangle using the difference in the coordinates. Now if we remember the trig function, tan theta equals opposite over adjacent, then we can see that actually for our situation that tan theta would equal the difference in the y coordinates divided by the difference in the x coordinates. Therefore if we looked at the expression for the actual angle, then the angle would be the tangent of whatever this value here actually works out to be. Okay, so if we actually look at a real world example, so here we have some data for a segment. We can see that the hip has an x and y coordinate as indicated in the table here, and the knee has an x and y coordinate as indicated in the table here. The diagram shows those coordinates and also shows the difference values that would be obtained for the vertical side of the right angle triangle and the horizontal side of the right angle triangle. Now if we substitute those values into our trig equation. So tan theta equals, at the top we're going to have the vertical length of the right angle triangle, on the bottom we're going to have the horizontal length. Then we can see that actually by simple straightforward division, that we can locate what the tangent of that calculation will be. In this case we can see that we get a value of 3.46, so the angle whose tangent is 3.46 works out to be 73.87 degrees. Now obviously once we've obtained that value, we may need to adjust it according to any particular conventions that are being used, but the basic trig method for calculating an angle using 2D coordinates has been demonstrated to be a fairly straightforward method. This concludes this movie.